Welcome to this module on quantum error correction. In this video, we will talk more about details of the surface code. So just a recap of what we went through in the last video. The surface code is an error correction code that you construct on a 2D grid of qubits. So you lay out a d times d grids to get a distance d code. And in between all these data qubits, you place extra auxiliary qubits to measure these weight 4 stabilizers, Z1, Z2, and so on. It's interesting to note here that while you can now make an infinitely large grid of qubits if you want a very large distance code, the stabilizers are always local in the sense they only talk to 4 qubits in the vicinity. We call that a topological code. Generally speaking, the number of physical qubits that you need for a distance d surface code is, since it's a square, it's of d times d qubits, it's d squared, and then times 2 because of all the ancillary qubits. But you notice that there's one less auxiliary qubit than data qubits, so you get the number d squared minus 1. In the surface code, we can then detect the errors by running these circuits. And by looking at the outcome of the auxiliary qubit measurement, we can induce where did the errors occur. Before moving on to figuring out where the errors occurred, let's talk about the logical operators of the surface code. And the way we define that is that we can make what we call a horizontal cut on the surface code, where you take all the qubit along a certain axis, and you take this set operator, Pauli set, on each data qubit along this cut. You multiply them together. In this case, you will get 5 because this is a distance 5 codes. So you have set on this horizontal cut, and that's your logical set operator. For the logical x, you do the same, but a vertical cut, and you get x, and so on. And you will notice that these cut operators commute with all the stabilizers and anti-commute with each other as the logical Z and X mods do. It's interesting that we can actually place this logical cut wherever we want, as long as we go vertical for the X and horizontal for the Z. Let's look at an example. Let's take the smallest possible surface code that we can meaningfully define. That's a distance 2 surface code. Remember that in a distance d code, we can correct d minus 1 half errors. If you put d equals 2 into that and you round down, you get 0, meaning a distance 2 code cannot correct any errors, but it can detect errors. And to get an intuition for how the surface code works, this is very useful. So in this distance 2 code, we have a weight 4 stabilizer in the middle, x1, x2, x3, x4. And we have 2 stabilizers on the side, which are weight 2, that is Z1, Z3, and we have Z2, Z4. We define the logical operators with the cuts we just discussed. So we can either pick Z1, Z2, or Z2, Z3 as our logical sets, or we can pick x1, x3, or x2, x4 as our logical x. Note that we have this freedom of picking which one. That's something we can use to our benefit. So what we can do at the end of a quantum algorithm, if you want to measure your logical set, is you can measure both and you can check, are they the same? If they're not the same, then you know an error occurred. That can help you in decoding errors in your algorithm. With these logical operators defined, we can define the logical states. In this case, the logical 0 is the equal superposition between the states 0, 0, 0, 0 and 1, 1, 1, 1 of the data qubits. And we can then get to the logical 1 state by simply applying the logical x operator, either of them, to the logical 0 state. And you see that we end up then in the state 0, 1, 0, 1 plus 1, 0, 1, 0 with 1 over square root of 2 in front. This small distance 2 code was only recently experimentally realized in a number of experiments on superconducting qubits. And you can see the reference here if you want to know more about these experiments. Specifically, I show in the picture here also a chip where the first of these references was implemented on, which I'm holding in my hand on this picture. The actual qubits sit in the small chip in the middle, the gray one, and all the surrounding are sample holder that leads all the control signals from room temperature down to the superconducting qubit chip. Going to larger codes, I also want to mention some very recent results in implementing larger distance surface codes, again with superconducting qubits. There were some initial results on distance 3 codes that showed that you can really operate a surface code to correct errors. And more recently, the demonstration of a distance 5 code that outperformed the distance 3 code, showing that you really get to do better if you go to larger codes. Now, when you do these experiments on error correction codes in the surface code, an important job is to figure out where the error occurs on which qubits, and that's the job of the decoder. To show how this works in the surface code, let's imagine that we had a bit flip error on this center qubit. What that does is that you will see a pair of syndromes in the output of your auxiliary qubit measurements. Because now this bit flip code is part of 2 Z-type stabilizers. And in the surface code, errors generally show up in pairs, and the job of the decoder can generally be understood in how do we pair up the error syndromes to figure out where did the error occur. Similarly for the phase flip errors, that will also show up as pairs, but it gets tricky because sometimes errors don't show up as in pairs. For example, if you have a measurement error on your measurement qubit. So generally speaking, decoding is a very hard job, and really figuring out all the possible combination of errors that can lead to different syndromes is a hard job. And an active part of research is to figure out the best way of decoding surface codes or other type of error correction codes. With that, I want to summarize this video. So we looked at the surface code, which is currently one of the most successful error correction codes, which have been demonstrated in recent experiments. I should say there's also alternative platforms or approaches to quantum error correction that we have not studied in this video, but I encourage you to study that for yourself. 2 examples that recently showed nice experiments is the Bacon-Shaw code, which was implemented in trapped ions. That's the first experiment here. And then the GKP code, which is a bosonic code that was recently implemented with superconducting resonators. With that, if you will want to know more about advanced topics, you can look at the advanced topic video in this module.